Hello everyone, I hope you are doing really good. So today in this video we're gonna do the simulations for the microstrip patch antennas. The microstrip patch antennas are including the ground, and we have the substrate on top of that, and also we have the patch antennas, like the patch metal on top of that. For this kind of the antenna we have different kind of the excitations. So we have the prop fed that the coaxial length is coming from the bottom of the substrate, or we also have the edge feed which is coming from the side. So today we're gonna go over the edge feed antennas. Here I have put the general formulations for the width and the length of the patch antenna, but we also have the online microstrip patch antenna calculators that you can use them for calculating the width and length of the patch. So for our frequency, which is the 5 gigahertz, I will use the dielectric RO5880, and I have calculated all of them from the website. I just wanted to show you how we can do that. If you go to the Google, and if you Google microstrip patch antenna calculator, you will see the a couple of the online websites like the Microstrip patch antenna calculator in the Pasternak or Everything RF, or there are a couple of the others, even EMTAC. So I'm gonna click on the Pasternak website. So here you see the late web form, and you can put the dielectric constant. So as we are using RO5880, I'm gonna put 2.2. The dielectric height is 1.57, which is 62 mils, and it should be in millimeter. And also for the operating frequency, we're gonna go over the 5 gigahertz. So I just click on the calculate, and as you can see, the width of the patch is 23.7 and the length is 1970-31. So which is the same as here. So now we're gonna go over the simulations. As you see, this is the HFSS simulator. So where we first go over the drawing the structure, we can add the box from here, and it should be our ground. So for the ground, we need to define the ground, and I'm gonna put a square ground, and the parametric values of them will be minus W ground over 2. I want it to be completely symmetry on the coordination. So my Y will be minus WG over 2. And I just wanted to, for the ground, I just wanted to go from the back of the Z axis. So I'm going to put minus T. T is the thickness of the copper for the ground. So for the WG, I'm going to put 50 millimeter. And for the T is 0.017 millimeters. And the length in the X size will be WG. The length on the Y size will be again WG, because I want it to be a square, and the length for the Z size will be T as we defined here. So now I can go to the attribute and I can name it as a ground. For the material, I can put it as, for the ground is copper. We don't need to solve inside, and we can change the color to the similar to the copper color. So I just click on OK. So you can come here on the view, and you can click on the orient and feed all. You will see this is my ground. Now I need to add the box for the substrate. So I just again come here and click on the drop box. So again, for that one, it will be WG over 2, again, minus WG over 2. And now it will, the thickness of the ground was from minus T till 0. Okay, so now it will start from the 0 millimeter. And for this one, again, the length is WG, and this one is H for the substrate. So we define as 1.57 millimeter for the RO5880. We need to come here, name it as a substrate, and choose the material, which is RO5880, and we need to solve inside, so we don't need to check it. And for this material, the color is the almost the same green, dark green color, and we just need to click on the OK. And now you can see my substrate here. So now we have the ground, we have the substrate, we need to define the patch on top of that. So we come here and we define the position. So I'm gonna define the minus the width of the patch, actually VP over 2, and I'm gonna define the minus LP over 2. So now we need to start from the top of the substrate. So we have the edge substrate, and what's the VP? Like this is the width of the patch, which we calculated that before. I can show you here is 2370, and for the length is 19.31 millimeter. So here I'm gonna define it as 2317 millimeter, and for the length of the patch is 19.31 millimeters. Click on that. So the length, again, I'm gonna define the, as you can see here, the width of the patch on the X direction, the length of the patch, and the Y direction, and the thickness of the patch sub is T, as you can see here. So now we again need to go to the attribute. We call it as patch. So we change the material to the copper. We don't need to solve inside, and just need to change the color to be similar to the copper color. Click on OK, and now you can see this structure. So now we need to feed this antenna. For feeding this antenna, I need to put a trace like from this side. And the only thing that I need to mention here, so normally we need to calculate the impedance at the edge of the substrate, like here. Then I can put the trace with the specific width related to that substrate. Then we can connect it here. But the point is, we want it to be connected to the 50 ohms. So for the 50 ohms, I can do a couple of the things. One of the methods that I can do, actually there are other methods, but I just wanted to explain what I'm gonna do to do. So normally, like the practically, if you wanted to have a 50 ohms of the input impedance for your antenna, you need to cut this here and add a trace, and then like the 1/3 of this length will be close to the 50 ohm. I don't want it to say exactly 50 ohm, but it will be close to the 50 ohm. So practically this is true, but if you wanted to make it better, you can optimize it. So I just wanted to do it add the trace and cut here like a 1/3 of that, and then add it. I will show you in a couple of the minutes. So now I need to add the feed line. I click on the drawbox. So come here. It should be W feed over 2. So for the Y direction, I'm gonna keep it 0 millimeter, and I'm gonna go to back. And for the Z direction, it will be edge sub. So here, what is the WF? You can also calculate it. You can go to the website. Yeah, a strip line calculator. If you click on that, again, you will see a couple of the online websites. I just clicked on the strip line impedance calculator. So I come here, again, add the dielectric constant 2.2. I add the trace width 2.1 and the dielectric height, which is 1.57. And you can also add the trace thickness. I'm gonna put 0.017 millimeter. So I click on the calculate, and it's showing 5108. So you can change this. If you wanted to go to the upper, decrease it. If you wanted to go to the down, like 2.2, 49, 2.15, let's say 50 ohm of the result. So 2.15 is the trace width. So here, what is this? It is 2.15 millimeter. So I click on OK, and here I can again the length, the width of that one is WF. So it will go from the 0 exactly till here. Okay, so the whole size was WG, and it will go from the 0 to the minus WG over 2. So it will be minus WG over 2. As you can see here, it's come to here, and the thickness will be T. Okay, so we can go to here, we can define the, name it as a feed. So material is copper. I don't need the solvent slide, and we can change the color and click on OK. So now you'll see the feeding from here. And as I told you, exactly here, the input impedance is, it should be around the 200 ohms, but we need to be close to the 50 ohms. As I told you, it should be 1/3 of that. So we need to cut here. And for cutting there, again, I'm gonna define another box. So for this one, I will, for the width of this cut, I'm gonna name it as WC, which is in the X direction, WC over 2. And for the length of that one, I'm gonna first go to the edge of this, and then I will add the length. Okay, so then I will start from the minus LP over 2, and again for the Z it will start from H sub. So for this one, for now I wanted to put it as a 3 millimeter, which is a bit more than the width of this one. So here, exactly this point from here is the LG over 2, okay? So for this one, I'm gonna name it as WC, which is the width of the cut. And for this one, as I told you, is the 1/3 of that, which is LP over 3. So as you can see here, it's drawing the structure, and the thickness is T. I'm gonna call it as patch cut. So name it as copper. I don't need the solvent side, so I'm gonna just change it to the green, or sorry, red color, and click on OK. So as you can see here, this is the this is my antenna, so I need to cut here. So I come here, patch antenna, and select the patch cut, and you can go here, click on the subtract. You are subtracting the patch cut from the patch, and click just on OK. So you'll see the structure. So now they have the conflict with each other, so we need to unify them. I click on patch and click on the feed, which they have the conflict here, and I just unit them. Okay, so now everything is fine, and we are done with the overall design of the patch antenna. So we need to add the couple of the steps to simulate the antenna. First of all, I'm gonna go and add the excitation. For adding the excitation, you can use the rectangle sheets here. So what you do, you are defining the sheets here. So I always like to do the parametric, because at the end you can change them, or if you are making any change on the parameters, it will change for the whole system. So this is the best option that you can do. So I wanted to add the rectangular sheets for the port here, and as we know that it's starting from here to here is minus WG over 2, okay? And one by one, first of all, I wanted to add the width of the sheet, which is from here to here. So it will be minus W feed over 2, okay? Just a second, this is, okay. And minus W feed over 2, and for the Y, it will be minus WG over 2, and for the Z, I wanted to put it from the 0 millimeter. The axis that I need to use, it should be, oh, okay, so it says that we have to define the, okay, so this is WG/2. For the axis, we need to change it to the Y, okay, we wanted to do the shit in the XZ plane. So the width of that will be WF. If we go closer here, you will see the step by step of the drawing. So WF, okay, so it should be WF here, and this should be, okay. This should be, so we are starting from the 0, we are adding the T, we are adding the H sub, and we are adding another T. So I'm gonna add the T plus H sub plus T. So exactly it is showing here. So I'm gonna come here, I'm gonna name it as a port, and so we can change it like the any color. I'm gonna change it to the I don't know, maybe the red color. Okay, and okay again. Okay, so we define the sheet for the port. So what we need to do, we need to select the face. Okay, right click on that and selection mode, face, and click on that. Okay, so now we can right click on that, add the excitation. We can do a couple of the excitation. I'm gonna go with the modal lumped port. So you will see here in general, you name it, it's 50 ohms, and click on the next. You can define the new line. So it will start from this side to this side. So we define the port and next and just finish. Okay. So now we have the excitation, we have the patch, we need to define the radiation box here. Okay. If you wanted to check your excitation, you can come here, and this is your excitation as shown here. Okay. So right now we are going to the next step. We have to define the radiation box. I just click on this one. And so for this radiation box, you can do a couple of the things. So before going to that, I can say you that you can click on the create the region. And for the offset of the region, you can put, I don't know, maybe 50%. Okay. And you can click on that. This is the radiation box. Okay. That it's adding, but I want it to be like a bit thicker in this size. So what you can do, you can also change it from here in the X direction, or you can change it from here in the X direction. Let's say that you want to put the 100 in the Y direction. When you are changing that, it is changing here. Okay, 100. Oh, sorry. You have to keep it like, I don't know, 50 and 50. Then in the Z direction, maybe you can put it like 200, or I don't know, 500, let's say 500. Yeah, something like this. So for them, you can put it, I don't know, maybe 10, 10, 10, and 10. Yeah, that's enough. So normally you don't need to make it more because it will add the meshing, and you don't need to make it less. I think this size is enough for 10%. Yeah, it's enough for the sides and for the top and bottom. It's good. But anyway, it doesn't matter. So now we need to define the boundary condition for this radiation box. We just click on that, right click, add boundaries, and the radiation. So we define it as a radiation box. Red one, yes, it's okay. So if you check here, you have also the radiation box. Okay. So now that we defined all of them, we need to define the frequency that we wanted to simulate the structure. We just come here, analysis, and we are right click on that, add solution setup, and you can use the advanced analysis. So if you wanted to do a single simulation, you can do it here. You can do the multi frequencies, you can make it a broadband simulations. So I wanted to name it as a setup one. I'm gonna put like a the center frequency here, which is 5 gigahertz. Okay, and maximum number of the passes that I wanted to go is, I normally put it as 10. So I wanted to check the 10 passes. If it is converged in between of the 10 passes, then it's fine. If not, it will go to the 10th, and after the 10th pass, it will simulate the structure. So normally I put it as 10 in the options. I define the minimum number of the passes. At least I wanted to go over like 2 passes, and the conversion pass after 2 passes, I need the minimum number for the converged passes. So I'm gonna put it as 1 to keep it 1 because it's simple simulation. I just click on OK, and then now it is showing the frequency sweep. Okay, for the frequency sweep, I'm gonna define it from actually 2 gigahertz is more. So, but I wanted to just show the results. So it start this 3 because center frequency is the 5 gigahertz. I'm gonna put it like 3 gigahertz, and it will go to the 7 gigahertz, and I can reduce the number of the points to the 2.1, and I need to save the fields. So that's it. I just click on OK. So now I also have defined the simulations and everything. Now what we need to do is yeah, just the simulation of the structure. So we have all of them. I'm gonna change it to the XY. Yeah, we have all the things, and we need to go to the simulation and first validate that is there any missing part. No, we have the design setting, 3D model, boundaries and excitation, mesh operation, analysis setup, optimetrics, or the radiation. So everything is fine. We just click on the analysis. So I'm gonna stop the video to finish the analysis, and then I will continue the video. Hello again. So we are done with the simulation. So now we can see the results. I'm gonna first start with the defining the radiation box. So I'm gonna go and add the insert far field setup so I can add the infinity sphere. So for the start of the phi, we are going from minus 80, 180, and till the plus 180. So for the theta, I'm gonna again start from minus 180 till 180. So everything is good. Just click on OK. And then now I'm gonna start one by one. I'm gonna click on the result, terminal solution, then the data report. I'm gonna go over the rectangular plot so you can see all the informations here. You need to select the solution. So I'm gonna select this SWIP, and the domain is always SWIP. Click on the S11, S11, and then the DB form. Do we have any other families? No, just new report. As you can see here, this is my S11. It's resonating close to the 5 gigahertz, and it is under minus 10. But again, if you wanted to optimize it and make it better matching, so you can play with this distance or the length width that you see here, but it is matched because we use the 50 ohms, and we got these results. So our practical estimations for the 1/3 of the patch is really good, and this is showing under minus 10, which is acceptable for the radiation, and close to the 5 gigahertz. So there is a difference in the like the resonance frequency. It is not exactly on the 5 gigahertz, but it is resonating in the 5 gigahertz, but it's not exactly there. So this is because of the simulation values. So you can change them a bit to see how you can make it exactly on the 5 gigahertz. Okay. So the next step, we can see the VSWR value. Again, go to the same way, rectangular, and then now you can see the active VSWR. We can see the magnitude of that, and new report. If you click it, so it should be on mine under close to the 1 in the 5 gigahertz. So we're gonna add the marker here, and as you can see, there's 1.62, which is really good. It should be under the 3 to have a resonance or to be matched. So we saw them. We can see the radiation pattern. So we go to the far field report. We can see the rectangular plot. Yes, we can see here. So for the phi, I'm gonna click and select it as 0 and keeping the control and go over to 90 and click on the 90. As you can see here, it adds the 0 degrees and 90 degrees. So I'm gonna check that if it is under the dB. Yes. So new report. As you can see here, this is the radiation of our patch antenna. I'm gonna add the marker. So it is around 7.32 dB. It's a fine. It's a good results that we are getting here. Or if you wanted to see on the polar form, you can again come here, far field, and you can use this radiation pattern. Again, for the radiation pattern, you see all of them. Just click on the dB, and you need to select the phi. So I'm gonna choose the 0 again and go to the 90 first, keeping the control and selecting 90 and new report. As you can see here, this is the radiation. Again, you can like add a marker here and you will see the 7.33 dB of the radiation bugs of the gain. So again, what you can do, you can see the E fields on them. So if you wanted to see the E field and the patch antenna, you just need to click on that and right click and plot fields, E field. You can see the complex magnitude or you can see the vector. I prefer to see the vector. And here you just need to select the all objects. Just click on the done. As you can see, this is showing you the electric field. If you wanted to animate it, so then you can come here and click on this, right click and animate that part. So just animate it. You will see the animation. You can increase the speed of the animation and you will see how the field is going to the patch antenna. This is the method that it's going. So I'm gonna stop it here and what else? I'm just checking to okay, so everything is fine. You can also see the polar plot of the S11 here and the yeah, just see the on a Smith chart. So this is the result on a Smith chart. As you can see here, when it comes here, it's closing to the match and it has the match at the, if you can mark it and if you mark it, you will see that it is 4.92 gigahertz of the frequency. So this is the overall of the simulation for the patch antenna. And if you have any question, you can ask me. And thank you for watching. And you have a wonderful day. Bye bye.